Hi, I'm Professor Lyon. Welcome to the lecture series for ME 3613. This is the intro video, and I will note that I'm not going to go over the syllabus and issues like that because in the future I'm going to be putting these lectures on YouTube that people can use, and so that information won't be relevant. So we're just going to start digging into the content of where the course is going to go. So, what is our goal? We want to be able to develop, analyze, and solve ordinary differential equations. From a student perspective, what are you coming in with? You've probably just learned to solve ODEs, ordinary differential equations, in a service course by a highly unmotivated math professor who may not be all that useful at teaching on a good day. And to make matters worse, you had the math course in a winter semester, and you had the summer to forget everything. And so now here you are, and you're supposed to start applying this stuff. So that's a fun position to be in. So what are we going to do? Number one, we're going to remind you how to solve ODEs in the time domain, sort of the conventional way that you were shown. And we're going to show you next how machines actually respond, which is convolution, which is another way of getting the solution to ODEs, basically. Uh, and once you understand that, we're going to teach you a much easier approach to solving the ODEs using the Laplace transform and the frequency domain. And so for most of you, you probably had that in your math course as well. And you should have found it an easier way to solve the equations. We're just going to look at it in a little bit more depth. All right. As we do this, we're going to teach you how to analyze an ODE without solving it. Okay? Here's the reality. You can pretty accurately know the response of the differential equation to a given input without needing to solve it once you learn a few analytical tools. So we're going to start the class solving ODEs the hardest way possible. Then we'll start doing it with Laplace, and we're going to learn a bunch of analytical tools, and then we're not going to solve them the rest of the semester. And you will have a good understanding of what they're doing. That's the goal. The problem when you go to take your math course is they give you all these ODEs, and all it is equations and numbers. And we're going to look past all that, and you're going to find you can actually find an incredible amount of structure out of just the equation itself and figure out pretty much everything you need to do. All right. Once we get to that step, well, then we're going to start looking at how to generate our own ODEs. So we're going to look at translational systems, rotational systems, electrical systems, heat systems, and fluid systems. So we're going to have 5 groups of things we develop ODEs for. We're also going to introduce a little bit of linearization of nonlinear components in our models. Where do nonlinear things come up? Friction. Also on the fluid side, we're going to see them with pumps and with valves. So it's time to get to work. Let me just say the recommended text for this course. This is an excellent text. It's been around forever. Frederick Close Frederick and Newell, Modeling Analysis of Dynamic Systems. This is the 3rd edition. It's been around a long time. How long? As I recall, this is the text I had when I went to school. I think we used this. It's been around a long time. And if we didn't use it back then, we used it while I was in graduate school for teaching and stuff. So it's a very good textbook. Highly recommend it. We're going to use their stuff all through these lectures. And with that, time to get to work. The rest of the way, we're just going to be working with a document reader and me going over the content. So the good news is you're not going to have to see my face much anymore. Anyway, we'll talk to you soon. Bye now.